This is the first mini lecture for section 3.1 of the syllabus, which comes mostly from section 14.1 of the textbook. We're going to begin talking about probability now. So with the study of probability, we try to determine the likelihood of future events. For example, if we roll a pair of dice, how likely are we to roll an 8? What number are we most likely to roll, and so on. So we're trying to figure out how likely is it that a given event will occur in the future. How likely is a given person to get in a car accident? How much money are we likely to have to spend to repair their vehicle? How likely is a person given a certain history and background to have a certain medical condition? And what are we likely to spend for that? If I go to a casino and I play the slot machine, how likely am I to get the jackpot? If I play the lottery, how likely am I to win? Am I more likely to have spent more money than I got, or am I more likely to have gotten more money than I spent? And which would be the best games to play? So we're trying to make predictions about the future based on either past experience or some kind of theoretical consideration. And there are two ways of looking at probability. The first is the experimental view, in which you perform a large number of trials of an experiment, and then you use the results to guess the outcome of future trials. A simple example would be if we want to figure out how likely are we to get a heads up, I'll just toss a coin a bunch of times and count how many heads up I get. And I would use that to determine how likely I am to get a heads up in the future. This is the kind of probability that's used when they compute your insurance premium, right? At least it goes into that computation. They want to know how likely are you to get into a car accident or something like that. How likely are they to have to spend money on you? And they take basically like your class of people that all have about the same amount of expenditure that they're projecting, and they charge you a little bit more for that premium. But it's really important for them to compute that as closely as they can. So they have to look at a large number of individuals before they can have an insurance company. Okay, so then on the other hand, we have theoretical probability, in which we use reasoning and counting principles to predict the likelihood of an outcome or event before we've actually performed the experiment. So for example, when I toss a coin, I can say, well, I think each side is equally likely to come up, so the probability of getting heads up would be 1 out of 2, or 50%. Okay, so again, the experimental probability of an outcome X is the proportion of times the outcome occurs in a large number of trials of the experiment. So the probability of X is the number of times that X occurs divided by the number of trials of the experiment. So for example, suppose we want to determine the experimental probability of getting a heads up on a single coin toss by performing 50 trials of the experiment. So the idea is if we do this enough times, then this proportion should approximate some theoretical value. The more times, the better. And the only way to do this is just you have to perform the experiment a bunch of times. You could simulate it, of course, but I had my kids who are home from school. They don't have as much to do as they usually do. I had them do this for me. So there's their results. I told them, take a quarter, toss it 50 times, keep track of how many heads and how many tails you get. As you can see, they almost got 50-50. It was a little bit off. They got 51 heads up and 49 tails up. So here's what I do with that. So we had and I'm sorry, I have this written incorrectly. They performed 100 trials of the experiment. Make sure to make that edit. Okay, so they tossed the coin 100 times. They got a heads up 51 out of the 100 trials. So the experimental probability of getting a heads up is 51 out of 100. Or you can write that as 0.51 or 51%. Okay, you can express it all those different ways. That's the probability of getting a heads up computed experimentally. Now, of course, if I had done this, if they had done it maybe like 5 or 10 times, they wouldn't have gotten as accurate a result. Typically, the more trials you perform of the experiment, the closer the experimental probability will approach to some fixed ratio. Here what it approaches is the theoretical expectation, which is that it's 50-50, heads or tails. And if they had done this 1,000 times or 1,000,000 times, then they would probably be much closer than this. So, as you perform more trials, sometimes it gets further from what you expect, sometimes it gets closer. But in the long run, the more times you perform the experiment, the closer you're going to get to that expected value. And that's why you can't really run a small insurance company. You're going to have to be paying a lot to some people and nothing at all to other people. You have to be, that the company has to have a reasonable expectation that those are going to tend to average out, so that they don't end up losing more money than they're taking in. And most insurance companies operate on a pretty small margin. So, they don't really make a huge amount of profit. The whole point of insurance is that it averages the expenditures out across a large number of people. So, if there's a natural disaster or something, then that quickly overwhelms the insurance company, because then, the average goes way up. Okay, now let's determine the experimental probability of getting a 7 on a single roll of a pair of dice. And unfortunately, I had my helpers here to do this for me again. Okay, they did do this 50 times. And, so they noticed after they made their chart that 1 is not a possible outcome. And 2 is the smallest you could get when you're rolling a pair of dice. You could get as small as 2 and as large as 12. And you see they just wrote down, when they rolled the dice, they just put a mark every time they got that number. And then at the end, they tallied them up. So why don't we record this? I'll make a little table kind of similar to theirs. So let's see, they had 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, they got a 2 twice. They got 3 twice. They got 4 5 times. 5 they got 8 times. 6 they got 5. 7 they got 7 times. 8 was 4. 9 was 5. 10 was 6, 11 was 5, 12 was 1. And these should add up to 50 because they're supposed to have done 50 trials. Let's just double check that. Not that I don't trust them, but let's see here. So we have 10, 17, 22, 29, 33, 38, 44, 49, 50. Okay, so that works out. So it was 50 trials. So they did 50 trials. And we're trying to figure out how likely are we to get a 7 on the single roll. And they got a 7, it happened to be 7 times. So that's 7 out of 50. Which we could write as 0.14 or as 14%. So according to this experiment, you have a 14% chance of getting a 7 on a roll of 2 dice. Now, I'll mention that they were surprised by a couple of things here, because this was not as accurate as they thought it would be. If you've ever played a game with dice, you probably know that 7 is the most likely thing to roll. That's because there are more ways to roll a 7 than anything else. But you see, they got more 5s than 7s. That kind of surprised them. It also surprised them that they got so many 11s. But those things happen because this is random. But the more trials they performed, the closer the numbers would get to whatever they might theoretically expect. For instance, 7 would definitely emerge as the most likely thing to roll.